Okay, hi everyone, I'm Maria Schutte. I'm from the University of Oklahoma. And today I'll be talking about modeling starspot features on a solar-like star with an M-dwarf companion. And I'd first like to just thank all of my collaborators and also the organizers of this symposium for inviting me to talk and giving me this time to talk today. So getting started, the program that we use to model these spots is called STSP, and it can model the spot positions and sizes using the transit of a secondary object in front of the star. And it uses this secondary transit, as you can see in this video, to sort of probe the stellar surface features. And as the planet or other object crosses in front of the star, if there is a spot, as we wait for one to come around again, if there's a spot that is in the path of the secondary, there is this large or somewhat large bump in the light curve. And this allows us to then model the size of these bumps and also where on the star these bumps are located, thus giving us some idea of what the stellar surface looks like. So this program has been used before on the object HAP-P11, which is a K-dwarf. This was done by Brett Morris back in 2017, and this was shown to have many more spots than the sun, but at similar sizes. So this is a K-dwarf with a similar rotation period to the sun. And as you can see on the right here, this is an example of one of these light curves. This is from Kepler. This is Kepler data in black. The model from STSP being shown here in red. And then, as you can see in this sphere plot up here, each one of these spots corresponds to a bump here in the light curve. And overall, what they found for HAP-P11 was that the radii of these spots or spot groups were overall similar to the solar maximum, but there were many more of them, and the full extent does extend much farther than for solar maximum size spots. So for our research, we are looking at the star KY340, which is a Kepler object again. And this is a sun-like star. It has a similar effective temperature of about 5,800 Kelvin. And it's slightly larger in mass and radius, 1.1 times the mass and radius of the sun. So here on our toy HR diagram, it's slightly larger than the sun. So I've sort of exaggerated this, but it is slightly bigger than the sun. But as you can see from HAP-P11 down here, it is a K-dwarf, so it's a lower temperature, so it has a deeper convection zone, but it has the similar rotation period to the sun, about 29 days. But KY340, on the other hand, actually rotates about twice as fast as the sun. So it has a rotation period of about 13 days. And it's the secondary object is an M-dwarf in this case, and the period of that is actually 23 days, so they're not quite synchronized. So that is important to note. And it's also, I think we're getting towards sort of building a nice set of objects of different spectral types and also different rotation periods. So KY340, like I said, rotates twice as fast. And so when we look at sort of a preliminary result from one of these, one specific transit for this object, what we see is that on the right here, again, I've shown the light curve with the blue points being the Kepler data and the red curve being the STSP model. And the residuals are shown here at the bottom. And what you can see from both this light curve and from this sphere plot on the left here that shows where these spots are and how big they are. And the red line shows exactly the midpoint of this transit. these 4 spots in black are the 4 spots that we see in this transit. And this red spot, however, is actually a solar maximum spot. I've chosen sort of a pretty large solar maximum spot, just to sort of show in comparison that these spots are either on the order of or bigger than the spots that we see at solar maximum. And these blue lines show where the secondary crosses in front of the star. And as you can see, these spots are in the path of the secondary, which is important to note. We want that to be the case usually for these objects. So this is one example from one of there are only 34 full transits in the Kepler data. Here's sort of just the light curves of the other ones that we have completed from KOI 340. So this is just to show you sort of the full extent of every single one of these goes through STSP, and STSP is sort of computationally expensive. So this is sort of a lot of work to go through each one of these individually to make sure everything looks okay. And then if we then move on to sort of a large overview of what the spots look like on KOI 340, here we're now plotting a histogram of all of the radii from the completed transits I just showed. And as you can see from this black histogram for KOI 340 versus the solar maximum and solar minimum histograms, what we're tending to see for KOI 340 is larger spots. Now, we're tending to see, like I said, larger spots, but the histogram here is quite wide. And it's not full yet, but we're getting there. And then it is important to note that there are degeneracies in STSP between spot properties, since what we're actually looking at is the chord crossing length, not necessarily. So what can happen is we can actually get spots like this big one that appear to look the same in the light curve as these 2 smaller spots. And part of my work is going through and making sure that in each transit that most of the spots are located mostly within the path of the planet, because that's where STSP is really sensitive to. But it is important to note that we can get even larger spots if we consider the fact that maybe these spot groups are actually not quite in the path of the planet. It is also important to note, though, that we do assume circular spots with STSP, and that is another sort of limitation for the model. So if you're not fully convinced by just looking at the radii of the spot groups, we also can get the fractional spotted area of that ribbon where the secondary cross is. So basically, it's just the area in that ribbon that is covered by spots. And then we can assume that if no other spots occur on the path on the entire front hemisphere of the star, we get this lower limit number, this lower limit shown here. And looking at just the lower limit, you see that this is, again, the red line is the solar maximum, the very maximum. And we're either at that value or higher. And in some cases, we're actually up to values of like 5% fractional area. And if you instead consider the fact that possibly the entire front hemisphere of the star is spotted at a similar rate to that ribbon, what we actually get is these values up here. So that's the full error bar. And that's quite a large extent. So we're working on looking at the out of transit variability to sort of lower these upper limits down, sort of get a better idea of where the full extent is. But that's some future work. But if you just consider the lower limits, like I said, it is can be quite a large number for this object, KOI 340. And so some future work is just we've been awarded time on on LCO's MOSCAT 3 instrument, which is a simultaneous filter observation, so we can try to get some spot temperatures for these objects. And with that, I'll just leave my summary up here just for a second, and that's it.
Thank you very much. So there are several questions for you in the Slido, but we are running out of time, so I just ask one quick one. So someone is asking, what is the contrast for the spots you consider?
So STSP does not allow us to sort of change that. So we assume that the contrast is similar to sunspots.
Okay.
But that's something we're looking to sort of get down using the simultaneous filter observations, then we can get a better idea of that.
Okay, thank you. And then you can go to Slido and look at the other questions that are there for you.
Thank you.